Welcome to Software Engineering, Complete Beginner to Pro Guide. Before we dive in, consider this. Software is no longer just a tool. It is the invisible infrastructure of modern civilization. Every time you unlock your phone, transfer money, hail a ride, or stream a video, millions of lines of carefully engineered code hang silently behind the scenes. Mark Andreessen famously said, "Software is eating the world," and that was over a decade ago. Today, software doesn't just eat the world, it runs it. Understanding how to build software systematically, reliably, and at scale is one of the most powerful skills you can develop in the 21st century. That is exactly what this course is about. Whether you are a student, a career switcher, or a developer looking to level up, you are in the right place. Let's begin. Now let's look at the full roadmap of this course so you know exactly what journey you are embarking on. This lecture is structured into 6 chapters, each building on the last. We begin here with the foundations, what software engineering actually is, and where it came from. In Chapter 2, we explore the software development lifecycle, the structured process teams use to build software from idea to deployment. Chapter 3 covers requirements engineering, how we figure out what to build before writing a single line of code. Chapter 4 dives into software design and architecture, the blueprints of great systems. Chapter 5 focuses on software testing and quality assurance, because building it is only half the job. And finally, Chapter 6 addresses software project management, maintenance, and the modern practices shaping the field today. By the end of this course, you will have a complete, professional-grade understanding of how software is built in the real world. Before we go further, let's quickly establish who this course is designed for and what prior knowledge is helpful. This course is built for a wide audience. You do not need to be an experienced programmer to follow along. If you are a computer science or IT student, this course will complement your formal education perfectly. If you are a self-taught developer who codes but has never studied engineering principles, this will fill critical gaps. If you are transitioning from another career into tech, this gives you the professional vocabulary and mental models you need. Some basic familiarity with programming concepts like variables, functions, and loops is recommended but not strictly required. No advanced mathematics is needed. What matters most is curiosity and the willingness to think systematically. Everything else we build together from the ground up. So what exactly is software engineering? Let's start with the most authoritative definition available. The IEE, the Institute of Electrical and Electronics Engineers, defines software engineering as the application of a systematic, disciplined, and quantifiable approach to the development, operation, and maintenance of software. Let's unpack that carefully. The key words here are systematic, disciplined, and quantifiable. Systematic means we follow a structured process, not ad hoc guesswork. Disciplined means we apply professional standards and best practices consistently. Quantifiable means we can measure progress, quality, and outcomes. Software engineering is not simply about writing code. It is about applying engineering principles, the same principles used to design bridges, aircraft, and medical devices, to the creation of software. It treats software development as an engineering discipline with rigor, repeatability, and accountability. To really understand why software engineering exists as a discipline, it helps to compare it directly with informal programming. Think about the difference this way. Programming is the act of writing code to solve a problem, much like writing an essay to express an idea. Software engineering, by contrast, is the discipline of architecting, building, verifying, and maintaining large-scale software systems that are reliable, maintainable, and built to last, the way a civil engineer designs a bridge, not just a rope swing across a creek. A solo developer hacking together a weekend project is programming. A team of 50 engineers building a banking system used by 10 million customers is software engineering. The distinction matters enormously. Informal programming often works for small, short-lived tasks, but without engineering discipline, large software projects routinely run over budget, miss deadlines, contain critical bugs, and ultimately fail. Studies consistently show that over 60% of large software projects face significant problems, many of which are engineering problems, not coding problems. To truly appreciate software engineering, we need to understand why it was invented in the first place. And that story begins in 1968. By the mid-1960s, computers were becoming powerful enough to run complex programs. But there was a serious problem. Software projects were consistently failing. They were delivered late, over budget, riddled with errors, and nearly impossible to maintain. This crisis came to a head at a landmark NATO-sponsored conference held in Garmisch, Germany in 1968, where the term software engineering was formally coined. The conference acknowledged what became known as the software crisis, the inability of the industry to build reliable, large-scale software systems. Over the following decades, the field evolved rapidly. Structured programming in the 1970s, object-oriented design in the 1980s, the rise of the internet and open source in the 1990s, agile methodologies in the 2000s, and today's era of DevOps, cloud computing, and AI-assisted development. Each era brought new tools and practices in direct response to the challenges of the time. In our next chapter, we will explore one of the most important frameworks to emerge from this evolution, the software development lifecycle. In our previous chapter, we established what software engineering is and why it matters. Now, let's dive into one of its most foundational concepts, the software development lifecycle, or SDLC. The SDLC is a structured process that defines how software is planned, created, tested, and delivered. Think of it as a roadmap that guides an entire development team from the very first idea all the way to a work product in the hands of users. The lifecycle typically consists of 6 key phases: requirements, design, implementation, testing, deployment, and maintenance. Each phase has clear inputs, outputs, and responsibilities. Without this structure, software projects tend to go over budget, miss deadlines, or fail to meet user needs. By following the SDLC, teams can manage complexity, reduce risk, and deliver higher quality software consistently. As we walk through each phase today, keep in mind that the order and emphasis of these phases can vary depending on which process model a team chooses, something we will explore in depth very shortly. Let's zoom in on the very first and arguably most critical phase of the SDLC, requirements gathering. This is where we answer the fundamental question: what should the software actually do? During this phase, engineers work closely with stakeholders, customers, end users, business analysts, and managers to collect, analyze, and document their needs. Requirements fall into 2 broad categories. Functional requirements describe the specific behaviors and features the system must provide. For example, the user must be able to log in using an email and password is a functional requirement. Non-functional requirements, on the other hand, describe how the system performs rather than what it does. Examples include performance benchmarks like the page must load within 2 seconds, security constraints, scalability limits, or accessibility standards. A common mistake among beginners is focusing only on functional requirements and ignoring non-functional ones, which often leads to systems that technically work but are too slow, insecure, or difficult to scale. Proper requirements documentation, often captured in a software requirements specification or SRS document, becomes the contract between the development team and the client. Once we have a clear picture of what the system needs to do, we move into the design phase. Design is the bridge between requirements and code. It translates what the system must do into a blueprint for how it will be built. Design work happens at 2 distinct levels. The first is architectural design, also called high-level design, where we make big-picture decisions. Which components or services will exist, how they communicate with each other, which databases or external APIs will be used, and what overall pattern, such as client-server, microservices, or layered architecture, will guide the system's structure. The second level is detailed design, or low-level design, where we specify the internal workings of individual modules and classes, data structures, algorithms, database schemas, and interface contracts. Think of it this way: architectural design is like deciding a building will have 3 floors, a basement parking lot, and separate wings for offices and labs. Detailed design is like specifying the exact room layout, electrical wiring, and plumbing for each floor. Both levels are essential, and together they produce design documents and diagrams, such as UML diagrams and entity relationship models, that guide the implementation team. Now we understand what the individual SDLC phases are. Let's talk about how those phases can be organized into different process models. The oldest and most well-known model is the waterfall model, introduced by Winston Royce in 1970. In waterfall, the SDLC phases are executed strictly in sequence. You complete requirements entirely before starting design, complete design entirely before writing a single line of code, and so on. The process flows in one direction, like a waterfall. This model has real advantages. It is simple to understand and manage, it produces thorough documentation at each phase, and it works very well for projects where requirements are fully known and unlikely to change, such as government contracts, embedded systems, or safety-critical aerospace software. However, the weaknesses are significant. If a requirement is discovered to be wrong midway through implementation, going back upstream is extremely costly. There is also no working software visible to the client until very late in the project. In today's fast-moving technology landscape, where requirements evolve rapidly, pure waterfall can be dangerously inflexible. That said, understanding waterfall is essential because all other models are essentially responses to its limitations. Because waterfall's rigidity is a serious problem for many real-world projects, engineers developed alternative models that embrace iteration and feedback. Two important alternatives are the iterative model and the spiral model. In the iterative model, you divide the project into smaller cycles called iterations. Each iteration delivers a partial but working version of the software, which is then reviewed and improved in the next cycle. This means stakeholders see tangible progress early and can provide feedback that shapes subsequent iterations, drastically reducing the risk of building the wrong thing. The spiral model, proposed by Barry Boehm in 1986, goes further by explicitly incorporating risk management into every cycle. Each spiral loop consists of 4 activities: planning, risk analysis, engineering, and evaluation. Before committing to building anything, the team identifies the highest risk elements and creates prototypes or proofs of concept to validate assumptions. This makes the spiral model especially valuable for large, complex, high-risk systems. Think enterprise banking platforms or medical software. Both model a key insight. Software development is not a straight line but a series of informed, improving cycles. This iterative thinking is the philosophical foundation for the Agile movement, which we will explore next. The iterative thinking we just discussed evolved into one of the most influential movements in software engineering history, Agile. In February 2001, 17 software practitioners gathered in Utah and produced the Agile Manifesto, a short, transformative document that redefined how software should be built. The manifesto articulates 4 core values. First, individuals and interactions over processes and tools, meaning human collaboration and communication trump rigid bureaucracy. Second, working software over comprehensive documentation, a working prototype's worth more than a perfectly written spec that nobody reads. Third, collaboration over contract negotiation. Instead of defining every requirement up front in a legal document, work with the customer continuously throughout development. And fourth, responding to change over following a plan. Embrace change as a natural and healthy part of software development rather than fighting it. These 4 values are supported by 12 principles that emphasize delivering software frequently, welcoming changing requirements even late in development, maintaining a sustainable pace, and reflecting regularly on how to become more effective. Agile does not prescribe a specific process. Instead, it is a philosophy that various frameworks like Scrum and Kanban implement in practice. Agile is a philosophy, but teams need concrete frameworks to put it into practice. The 2 most widely adopted Agile frameworks today are Scrum and Kanban. Scrum organizes work into fixed-length iterations called sprints, typically lasting 1 to 4 weeks. Each sprint begins with a sprint planning meeting, proceeds with daily stand-ups, and ends with a sprint review and retrospective. Scrum defines specific roles: the product owner who manages the backlog, the Scrum Master who facilitates the process, and the development team who builds the product. It is highly structured and works best for teams building new features in a predictable rhythm. Kanban, originally from Toyota's manufacturing system, takes a different approach. Instead of fixed iterations, Kanban uses a continuous flow model with a visual board divided into columns such as to do, in progress, and done. Work items move across the board as they progress, and the key mechanism is work in progress limits, restricting how many tasks can be active at once to prevent bottlenecks. Kanban is more flexible and works especially well for support teams, operations, or projects with unpredictable incoming work. Both frameworks embody Agile values, but they suit different team dynamics and project types. As we move into the next chapter on software design principles and patterns, understanding these lifecycle models will help you appreciate why design decisions matter so much in iterative, fast-moving development environments. Welcome to Chapter 3. In the previous chapter, we explored the software development lifecycle and how teams plan, build, and deliver software. We dive deeper into how we actually design that software well. The foundation of good software design starts with the solid principles, 5 rules that every professional developer must know. S stands for single responsibility. Every class should have one job and one reason to change. O is open-closed. Your code should be open for extension but closed for modification. L is the Liskov substitution principle. Subtypes must be replaceable for their base types without breaking behavior. I is interface segregation. Don't force a class to implement interfaces it doesn't need. And D is dependency inversion. Depend on abstractions, not concrete implementations. Together, these 5 principles guide us toward code that is maintainable, testable, and scalable over time. Beyond solid, 3 more principles are essential for writing clean, professional code. First is DVRA. Repeat yourself. Imagine you write the same email validation logic in 10 different places. When the rules change, you have to update 10 places and risk missing one. DRY says, every piece of knowledge should have a single, unambiguous representation in your codebase. Next is KISS, keep it simple, stupid. The best solution is almost always the simplest one that works. Over-engineered code is harder to read, debug, and maintain. Think of it like building furniture. Don't add extra joints that serve no purpose. Finally, you aren't going to need it. Don't write code for features you think you might need someday. Build what is required now and extend later when the need is real. These three principles, combined with SOLID, form the philosophical backbone of clean software craftsmanship. Now let's look at two critical structural concepts, coupling and cohesion. Coupling measures how dependent one module is on another. High coupling is dangerous. If Module A knows the internal details of Module B, a change in B can break A. We always aim for low coupling, where modules interact through well-defined interfaces and know as little as possible about each other's internals. Cohesion, on the other hand, measures how focused a module is on a single purpose. Low cohesion means a module does many unrelated things, like a Swiss Army knife class that handles user authentication, database queries, and PDF generation. High cohesion means a module does one thing and does it well. The golden rule is, design modules that are loosely coupled and highly cohesive. When you achieve this, your codebase becomes modular, easy to test, replace, and extend without cascading side effects throughout the system. With solid design principles in hand, we can now look at the bigger picture, software architecture. Architecture defines how the major components of a system are organized and how they communicate. The three most commonly discussed styles are monolithic, layered, and microservices architectures. A monolithic architecture bundles everything, UI, business logic, and data access, into one deployable unit. It's simple to develop initially, but becomes difficult to scale and maintain as the codebase grows. A layered architecture, also called N-tier, separates concerns into distinct horizontal layers: presentation, business logic, and data. Each layer only talks to the one directly below it. This improves organization but can still become a bottleneck. Microservices architecture breaks the application into small, independently deployable services, each responsible for a specific business capability. Netflix and Amazon famously use this approach. It offers excellent scalability and resilience, but introduces operational complexity. Choosing the right architecture depends on your team size, project scale, and long-term goals. One of the most widely used architectural patterns, especially in web development, is MVC, Model View Controller. MVC elegantly solves the problem of mixing data logic, display logic, and user input handling in the same code, which quickly becomes a tangled mess. Here is how it works step by step. First, the user interacts with the view, the user interface, such as clicking a button or submitting a form. Second, that interaction triggers the controller, which acts as the traffic manager. The controller interprets the user's input and decides what to do next. Third, the controller communicates with the model, which represents data and business logic. It might fetch records, a database, or perform a calculation. Fourth, the model returns the updated data back to the controller. Fifth, the controller passes that data to the view, which renders it for the user. This clean separation means your designers can work on the view, your back-end developers on the model, and routing logic stays neatly in the controller. Frameworks like Django Ruby on Rails, Spring MVC, and Laravel all implement this pattern. Now we arrive at one of the most celebrated topics in software engineering, design patterns. In 1994, four authors, Gamma, Helm, Johnson, and Vlissides, known as the Gang of Four, published a landmark book cataloging 23 reusable solutions to common software design problems. These are not libraries you import, they are proven blueprints for structuring your code. The patterns are grouped into three categories: creational, structural, and behavioral. Let's start with creational patterns, which deal with how objects are created. The singleton pattern ensures that a class has only one instance throughout the application, useful for things like a configuration manager or a logging service. The factory pattern provides an interface for creating objects without specifying the exact class to instantiate. Imagine a shape factory that returns a circle, square, or triangle based on input. The builder pattern constructs complex objects, step by step, separating construction logic from the final representation. Think of configuring a complex HTTP request or building a database query. Structural patterns focus on how classes and objects are composed to form larger structures. Two of the most practical ones are adapter and decorator. The adapter pattern acts like a real-world plug adapter. It allows two incompatible interfaces to work together. Imagine you have a legacy payment system that expects data in XML format, but your new service produces JSON. An adapter class wraps the old system and translates the data. letting both sides communicate without modifying either. The decorator pattern dynamically adds behavior to an object without altering its class. Think of a coffee shop. You start with a basic coffee object, then decorate it with milk, sugar, and whipped cream. Each decorator adds description while wrapping the original object. In the code example here, a base text logger is decorated with a timestamp decorator that prepends the current time to every log message. This is far more flexible than subclassing, because decorators can be combined in any order at runtime. Finally, behavioral patterns define how objects communicate and assign responsibilities between them. Two of the most important are observer and strategy. The observer pattern implements a publish-subscribe mechanism. One object, the subject, maintains a list of dependents called observers and notifies them automatically when its state changes. You see this everywhere. When a YouTube channel uploads a video, all subscribers get notified. In code, a stock market subject notifies all registered portfolio observers when a price updates. The strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. Instead of hard-coding a sorting algorithm, you inject a sort strategy, and you can swap bubble sort for quicksort at runtime without changing the calling code. This is incredibly powerful for payment processing, where you might switch between PayPal, Stripe, or credit card strategies. As we wrap up this chapter, you now have a strong foundation in design principles and patterns. In our next chapter, we'll apply this thinking to software testing and quality assurance, ensuring the beautifully designed code we write actually works correctly. Welcome to Chapter 4, Software Testing and Quality Assurance. In the previous chapter, we explored software design principles and patterns, the blueprints that guide how we structure our code. But even the most elegant design can hide subtle bugs. That is exactly why testing exists. Software testing is the process of evaluating a system to detect differences between expected and actual behavior. There are two core concepts every engineer must understand. Verification asks, are we building the product right? Meaning, does the software conform to its specifications? Validation asks, are we building the right product? Meaning, does the software actually solve the user's real problem? Think of building a bridge. Verification checks that the steel beams meet engineering specs, while validation confirms the bridge connects through cities people actually need to cross. Without rigorous testing, bugs slip into production, costing companies enormous time and money. The famous 2002 NASA Mars Climate Orbiter failure, caused by a unit conversion bug, cost $327 million. Testing is not optional. It is a professional obligation. Software testing is not a single activity. It happens at multiple levels, each targeting a different scope of the system. Imagine a pyramid with 4 layers. At the very base, we have unit testing, testing individual functions or methods in complete isolation. These tests are small, fast, and numerous. They form the foundation of your test suite. Moving up, integration testing verifies that multiple units or modules work correctly together. For example, does your payment service communicate properly with the order management service? Above that, system testing evaluates the entire application as a whole against the full set of requirements. This is where end-to-end scenarios are tested in an environment that mirrors production. At the very top of the pyramid sits acceptance testing, specifically user acceptance testing, or UAT. Real stakeholders, or end users, confirm the software meets their business needs before it goes live. The pyramid shape is intentional. You should have many unit tests, a moderate number of integration tests, fewer system tests, and a small number of acceptance tests. This balance keeps your test suite fast, reliable, and cost-effective. Inverting this pyramid, relying too heavily on slow end-to-end tests, is a common anti-pattern known as the ice cream cone. Beyond testing levels, engineers also choose different testing techniques based on how much they know about the internal workings of the system. There are 3 main approaches. Black box testing treats the software as a completely opaque system. The tester knows nothing about the internal code structure. They only provide inputs and observe outputs. This approach closely simulates how real users interact with the system and is excellent for functional testing and finding usability issues. However, it cannot guarantee internal code coverage. White box testing, on the other hand, gives the tester full visibility into the source code, algorithms, and architecture. Testers can design test cases that exercise every branch, loop, and condition in the code. This technique achieves high code coverage, requires deep technical knowledge, and may miss higher-level business logic gaps. Gray box testing sits in the middle. The tester has partial knowledge of the internals, such as database schemas or API specifications, but does not directly with source code. This is very common in integration testing and security testing scenarios. Most professional test strategies combine all 3 techniques, applying each where it provides the greatest value. Now that we understand the types and levels of testing, Let's explore a powerful development methodology that integrates testing into the very act of writing code. Test-driven development, TDD. TD flips the traditional workflow on its head. Instead of writing code first and tests later, which often means tests never get written at all, TDD demands that you write a failing test before you write a single line of production code. The TDD cycle has 3 phases, often called red, green, and refactor. In the red phase, you write a test for a piece of functionality that does not yet exist. You run it, it fails. This is expected and healthy. The failing test is your specification. In the green phase, you write the minimum amount of code necessary to make that test pass. No more, no less. Resist the urge to over-engineer at this stage. Finally, in the refactor phase, you clean up and improve the code, eliminate duplication, improve naming, apply design patterns while keeping all tests green. Then the cycle repeats. TDD produces code that is inherently testable, forces developers to think about interfaces before implementation, and creates a comprehensive regression suite as a natural byproduct. Studies by IBM and Microsoft have shown TDD reduces defect density by 40 to 90%, at the cost of only a 15 to 30% increase in development time. Writing tests manually is valuable, but running them manually is not scalable. This is where test automation becomes essential. Automated testing uses frameworks and tools to execute tests automatically, compare actual results to expected results, and report failures, all without human intervention. For unit testing in Java, JUnit is the industry standard. For browser-based end-to-end testing, Selenium WebDriver allows you to script user interactions across real browsers. Python developers often use PyTest, while JavaScript teams rely on Jest or Cypress. Let's look at a JUnit fifth example. We have a calculator class with an add method. Our test class uses the @test annotation, calls calculator.add with 2 and 3, and asserts the result equals 5 using assert equals. This single test can now be run automatically every time code is committed. This is where CI/CD, continuous integration and continuous deployment, comes in. Every code push triggers a CI pipeline. The code is compiled, all automated tests are executed, and if any test fails, the pipeline stops and the team is immediately notified. Tools like GitHub Actions, Jenkins, and GitLab CI make this seamless. The combination of TDD, automated tests, and CI/CD creates a safety net that lets teams deploy with confidence multiple times per day. Testing tells us whether specific behaviors are correct, but how do we measure the overall quality of a software system? This is where software quality metrics come in. Metrics give us objective, quantifiable data to track quality trends and make informed decisions. Let's look at 4 essential metrics every engineer should know. Code coverage measures the percentage of source code lines or branches executed by your test suite. A coverage of 80% is commonly cited as a reasonable target, though 100% coverage does not guarantee bug-free software. Defect density counts the number of confirmed bugs per 1,000 lines of code, or KLOC. Industry benchmarks suggest fewer than 1 defect per KLOC for high-quality software. Cyclomatic complexity, developed by Thomas McCabe, measures the number of linearly independent paths through a function's control flow graph. A complexity score above 10 signals that a function is too complex and should be refactored. Mean time to failure, or MTTF, measures system reliability, the average time between failures in production. Higher MTTF means better reliability. Tools like JCoco measure code coverage, SonarQube tracks density and complexity, and New Relic monitors production reliability. Monitoring these metrics continuously, not just at release time, is the hallmark of a mature engineering organization. Individual metrics are useful, but a comprehensive quality framework gives us a complete picture. The internationally recognized standard for software product quality is ISO 25000, published by the International Organization for Standardization. ISO 25010 defines major quality characteristics, each with its own subcharacteristics. Functional suitability asks whether the software does what users actually need. Performance efficiency covers response time, throughput, and resource utilization. Compatibility ensures the system works alongside other software and in diverse environments. Usability measures how easily and effectively real users can operate the system. Reliability covers tolerance, availability, and recoverability after failures. Security addresses confidentiality, integrity, and protection against unauthorized access. Maintainability is critically important for long-term projects, captures how easily the software can be modified, tested, and analyzed. Finally, portability measures how easily the software can be transferred to different environments or platforms. ISO 25010 is used as the quality checklist for enterprise procurement, compliance audits, and quality management systems worldwide. As we move into our final chapter on practical software engineering, you will see how these quality characteristics translate into real-world team practices, DevOps, culture, and professional engineering standards that drive successful projects. Welcome to Chapter 5, where we bring everything together and see how software engineering works in the real world. In the previous chapter, we covered testing and quality assurance, ensuring our code is correct. But how do we actually ship that code reliably and repeatedly? That is where DevOps comes in. DevOps is not just a set of tools. It is a cultural philosophy that breaks down the traditional wall between development teams, who write the code, and operations teams, who run the infrastructure. By fostering shared responsibility, continuous communication, and automation, DevOps enables organizations to deliver software faster, more reliably, and with fewer failures. Companies like Amazon, Netflix, and Google deploy code hundreds or even thousands of times per day, all made possible by DevOps culture and practices. At the heart of DevOps is the CI/CD pipeline, continuous integration and continuous delivery. Let me walk you through each stage. First, a developer commits code to a shared repository like GitHub. This immediately triggers the CI pipeline. In the build stage, the code is compiled or packaged automatically. Then automated tests run, unit tests, integration tests, the kinds we discussed in Chapter 4. If any test fails, the pipeline stops and the developer is notified immediately. Once all tests pass, the artifact is pushed to a staging environment for further validation. Finally, in continuous delivery, the approved build is automatically deployed to production, sometimes with a manual approval gate for safety. This entire process can take minutes, replacing what used to take days of manual coordination. The result is faster feedback, higher quality, and confident deployments every single time. Knowing how to build software well is only half the battle. You also need to manage the project effectively. One of the most practical skills in agile teams is estimation. Rather than guessing in hours or days, modern teams use story points, a relative unit that captures effort, complexity, and uncertainty together. For example, a simple bug fix might be 1 story point, while a complex new feature could be 13 points. Teams use a technique called planning poker, where each member simultaneously reveals their estimate on a card, preventing anchoring bias. Over several sprints, a team learns its velocity, how many story points it completes per sprint on average. This historical velocity becomes the most reliable forecasting tool available. Good estimation does not mean being perfect. It means being consistently calibrated, learning from past data, and building trust with stakeholders through predictable delivery. Now let us talk about something every experienced engineer has encountered: technical debt. Technical debt is the implied cost of choosing a quick, convenient solution now instead of a better, more robust approach that would take longer. Think of it like financial debt. You get something immediately, but you pay interest over time in the form of slower development, harder maintenance, and more bugs. For example, duplicating code instead of refactoring it into a shared function saves time today, but creates a nightmare when that logic needs to change in 6 different places. On the other side, proactive refactoring, restructuring existing code without changing its behavior, reduces this debt and keeps the codebase healthy. The key lesson from industry is this: technical debt is sometimes acceptable as a deliberate trade-off, but it must be tracked, communicated to stakeholders, and regularly paid down before it becomes unmanageable. History is one of the best teachers in software engineering. Let us look at some of the most consequential software failures ever recorded and what the industry learned from them. In 1996, the Ariane 5 rocket self-destructed 37 seconds after launch due to a floating point conversion error, reusing software from Ariane 4 without validating it for the new context. The cost, $370 million. In 1999, NASA launched the Mars Climb Orbiter because one team used metric units while another used imperial, a unit mismatch costing $327 million. Then in 2013, the launch of healthcare.gov in the United States became infamous for crashing under load immediately, exposing poor capacity planning, insufficient integration testing, and lack of coordination across dozens of contractors. Each of these disasters shares a common thread: failures of communication, assumption, and insufficient validation. These are not just historical footnotes, they are our active reminders of why every practice we have covered in this course matters. Drawing from everything we have covered: requirements, development processes, testing, DevOps, and real-world case studies, let us close this chapter with a practical checklist that every professional software engineer should internalize. These are not theoretical ideals, they are battle-tested practices that distinguish high-performing teams from struggling ones. First, always define and document requirements before writing a single line of code. Second, choose your architecture and design patterns deliberately, not by habit. Third, Write tests alongside your code, never as an afterthought. Fourth, use version control and peer code review without exception. Fifth, automate your build and deployment pipeline to eliminate manual errors. Sixth, track and actively manage technical debt before it accumulates. And seventh, conduct retrospectives and postmortems, learning from both successes and failures. In the next and final chapter, we will consolidate all of these ideas into a comprehensive summary and map out your path forward as a software engineer. Welcome to the final chapter of our software engineering course. The past 5 chapters, we have taken a complete journey from the very foundations of software engineering all the way real-world professional practices. We started by understanding what software engineering is and why it matters. We then explored the software development lifecycle, covering planning, analysis, design, implementation, testing, and maintenance. From there, we dived into design patterns and software architecture, learning how experienced engineers solve recurring problems with proven solutions. We covered software testing and quality assurance, understanding that shipping reliable software is not an accident, but the result of disciplined verification. Finally, in our previous chapter, we connected all of these concepts to the real world through agile methodologies, DevOps practices, CI/CD pipelines, and team collaboration. Today, we consolidate everything, extract the most important lessons, and map out your path forward as a software engineer. Before we part ways, I want to leave you with the single most important mindset shift that separates a great software engineer from an average one. Software engineering is not just about writing code that works. It is about writing code that others can read, maintain, extend, and trust. The legendary computer scientist Donald Knuth once said, "Programs are meant to be read by humans and only incidentally for computers to execute." This captures the engineering mindset perfectly. Every decision you make, your variable names, your architecture choices, test coverage, your documentation, is ultimately a communication act, your future self and your teammates. Embrace this mindset, and every technical skill you learn will compound into something far more powerful than any single tool or framework. Now that you have a solid foundation in software engineering, the question is, what comes next? The field is vast, and continued growth requires deliberate practice and structured learning. Here is your action plan. First, pick one side project and apply the full SDLC, from requirements gathering to deployment. Nothing replaces hands-on experience. Second, study its 2 classic design patterns in depth by implementing them yourself. Third, set up a personal CI/CD pipeline using GitHub Actions or GitLab CI for your projects. Fourth, read the book Clean Code by Robert C. Martin. It will change how you write every line of code. Fifth, explore certifications such as AWS Certified Developer or the Professional Scrum Master credential to validate your skills. And finally, stay curious. Follow engineering blogs, contribute to open source, and never stop asking why. The best engineers are lifelong learners. Thank you for completing this course, and I look forward to seeing what you build next.